you go.
Thank you. Good morning. Last class, there was a slide missing, and Greg from the American Ceramic Society resent the lecture on thermal expansion. So it was this slide, which I think was number 61. For some reason, I had accidentally put it in hidden mode and didn't show up. I fixed it. So very briefly on thermal expansion and anisotropy, polycrystalline ceramics and refractories. There's thermal expansion and anisotropy between the grains that are adjacent to each other. Intergranular thermal stresses develop. These thermal stresses lead to microcracking. And I mentioned that microcracks decrease strength, but they increase thermal shock resistance because cracks, when they grow, dissipate stored elastic strain energy. So this is the slide that was missing. And they're just different ceramic and refractory materials, and their crystal structures are shown. So if it's not cubic or not vitreous, the ratio of the thermal expansion in the different directions, that ratio is going to be greater than 1. So in aluminum, it's 1.09. Graphite, it's 1.5. So anytime this ratio is greater than 1, you have the possibility of microcracking. Fused silica is 1-to-1. MgO is cubic, it's 1-to-1. So in a single crystal material, that polycrystalline, one crystal type, anytime it's a crystal structure that's not cubic or it's not amorphous, you have the possibility of microcracking. And then I showed this last time, 2 different phases, like a mullite and silica or aluminum and mullite. The delta L over L, the mismatch is there. So that leads to microcracking. And then composite materials like an MgO carbon material, all of these composites have a thermal expansion mismatch, so they can all lead to microcracking. So we concluded that almost all heterogeneous refractories are susceptible to microcracking and suffer microstructural damage. And it starts on a fired brick on the first cooling cycle, and as you thermally cycle it, it just continues. So that was the missing slide from thermal expansion. So you should have that right now. And then we were in the middle of the lecture on thermal conductivity. I'll finish that up, and we'll need to start, at least get started on fracture behavior. And that'll be the last property before we start thermal shock theory next week. So there are 2 types of ceramic microstructures that influence the thermal conductivity, type 1 and type 2. Type 1 is a ceramic that's highly porous, and basically that's called a defective microstructure. And type 2 are ceramics that are dense with a more ordered microstructure. So highly porous ceramics and refractories have low thermal conductivities, and the conductivities tend to increase with temperature due to radiation across pores. So last class, we did develop an equation for solid state thermal conductivity, photon conduction, and then we developed an equation for photon conductivity for transparent materials. And then we developed a second equation for photon conductivity between boundaries, which is basically a pore and a refractory material. So we developed those 3 equations, and we noted that when there's porosity present, radiation across pores increases with temperature. So ceramics with dense ordered microstructures, low porosity, have higher thermal conductivities. The conductivities first start to decrease with temperature. That was that 1/T, 1/temperature relationship. And then they may increase due to radiation effects at higher temperatures. So type 1, highly porous materials, the grain-to-grain contact is poor due to the high porosity. Uh, Solid state conductivity to the phonons, it tends to be small because of the effective microstructures. And then the photon component of thermoconductivity is the dominant mechanism. And we noted that electromagnetic radiation is proportional to T to the fourth power. So there's a rapid increase with temperature in the radiation. So there's a rapid increase in conductivity with temperature. So these are insulating materials that overall have low thermal conductivities, and the photon heat transfer through the pores is important. The type 2 materials that are dense, good grain-to-grain contact, low porosity, photon component tends to dominate the thermal conductivity. The phonon scattering increases with increasing temperature, and therefore there's a thermal conductivity decrease with increasing temperature. And basically, above room temperature, it's that 1/T relationship until you get to a higher temperature where lattice scattering takes over and the conductivity tends to become constant. So the photon component, if there's porosity, starts to dominate at much higher temperatures. Again, irradiation is proportional to the T to the fourth power, so that causes a rapid increase in the radiation portion. So type 2 materials overall have high thermal conductivities, a combination of phonon conduction and then radiation or photon heat transfer at the higher temperatures. So relative to a ceramic microstructure, the microstructures of refractories are more complex. They have multiple phases present. They have defects which are either intentional or intrinsic. So in general, refractories tend to have lower thermal conductivities compared to normal ceramic materials because they have a more defective microstructure. And this more complex microstructure makes the trends in thermal conductivities of refractories more difficult to predict. And they have a complex bulk density porosity relationship. So they're just harder to see trends in these materials. The defect structures, you have intergranular pores. These are located in the matrix that separates the aggregates. So the bonding matrix has pores that are either open or closed. You have intragranular pores. These are located in the aggregates. Again, these can be open or closed. You have microcracks. Microcracks can be located in the matrix, the aggregates, or at the bond between the matrix and the aggregates. So interfacial or transgranular microcracks. Impurities, solid phases with chemical or crystalline characteristics different from the matrix or the aggregates. These can be intergranular, intragranular, they can be isolated, they can be continuous. So there's many possibilities to make a refractory microstructure more complex. Plus you have the different types of matrix phases that can be present. So the bonding matrix phases that are typical of refractories are shown here. Ceramic bonding, a silicate glass or aluminosilicate phase. These are amorphous. They melt and then solidify. So they melt at the firing temperature, the use temperature, and then solidify upon cooling. You can have amorphous or aluminosilicate phases. Direct bonding. This is where you have solid crystalline phases in contact with each other. That's as a result of sintering or solid state reactions. Hydraulic bonding, um, you have a mixture of multiple types of hydrated phases due to the use of a refractory cement. And those are usually water-based. Resin bonded, this is quite common in composites with carbon. So you have resin and carbon residues as a result of coating of the resin. And then there's different types of chemical bonding. So various chemical compounds bond by various types of chemical reactions. So refractories are actually quite complex. So this is a typical refractory microstructure. You have your coarse aggregates. You have your bonding matrix. You have pores within the coarse aggregates. You have pores in the matrix, intergranular porosity. And then due to thermal expansion mismatches, you have microcracks forming. And these are shown at the interface between a coarse aggregate and the bonding matrix. So that's a typical refractory microstructure. So if we look at a plot here of conductivity versus temperature. So this is actually log of conductivity versus log of temperature. The units for conductivity here are in the watt units and temperature is Kelvin. Here's temperature in degrees C, and then thermal conductivity on a log scale here. So materials like graphite, carbon. Over here we have alumina, MgO, and quartz. These are our polycrystalline refractory type materials. And you can see as the temperature goes up, the conductivity is going down. And they're following this 1/T relationship. So that's phonon conduction, solid state thermal conductivity. The conductivity is proportional to 1/T, basically from room temperature to some temperature where the conductivity tends to level off. And if you take the log of each side of this proportionality, the log of the conductivity is proportional to -1 times the log of temperature. So these should have a slope of -1, and on this plot, they actually do have a slope of -1. So these equations actually work quite well. And then these other materials, vitreous or fused silica, quartz, fine grain size zirconia, they start to show an increase in thermal conductivity at high temperatures, and that's due to photon conduction. So the conductivity due to radiation and the equations we developed, K is proportional to T cubed. So the log of K radiation is proportional to 3 times the log of the temperature. So these should have a slope of +3. And on these plots, these are +3. So the equations we developed for phonon conduction and photon conduction actually correctly predict the trends in these materials. So on this chart, graphite is a high thermal conductivity material. There's carbon, which is probably an amorphous carbon, MgO and alumina, and CaO. They're all higher conductivity refractories. Mullite, zircon, and zirconia tend to be lower. Vitreous silica starts out low because it's a glass, it's an amorphous structure, but then the photon or radiation conduction takes over. And we didn't mention that glasses have much lower phonon conduction than crystalline materials because of the highly disordered structure. So this is the same plot, thermal conductivity versus temperature. And these are the materials on that diagram. And at low temperatures, um, this is lattice or solid state or phonon conduction. And the D just means that dominates is the most dominant mechanism. And in these materials like vitreous silica, M means minor. And in a material like steel, it's undetected. A few of these materials are slight semiconductors. CaO and mullite, it's possible. And in material like titanium carbide or tantalum carbide, they're semiconductors. It tends to dominate. ZrO2 can also be a semiconductor. And then for metallic conduction, the steel uh, electronic conduction dominates. And then at high temperatures where photon conduction can take place, these materials that are more transparent, that mechanism dominates. So D is a dominant mechanism, M is minor, P is possible, Q is questionable, U is undetected, and N is none. I'm not sure in this table what the difference between U and N is, but in either case, there's no contribution to conductivity. So this is another reference table, different kinds of refractory materials and their thermal conductivity at 3 different temperatures, 100 degrees C, 500 degrees C, and 1,000 degrees C. And this is in watts per meter degrees K. So a material like magnesium oxide has a high thermal conductivity, and then you see it decreases with increasing temperature. And that's that 1/T relationship. Silicon nitride and silicon carbide also have high thermal conductivities at room temperature, and then they decrease with increasing temperature. Beryllium oxide, very small atoms, tight crystal structure, has a very high thermal conductivity, and that decreases with temperature. This material is not really used because it's toxic, but it does have a very high thermal conductivity as we would expect. And then some materials like mullite are quite a bit lower, a more complex structure. And so are the spinels, they're quite a bit lower. So this is just a reference table. And you can see that the normal materials, some of the conductivities are around 3, they go up to about 50. So that's pretty much the range for these materials, excluding beryllium oxide. So thermal conductivity for basic refractories. These materials normally have, let's say 0 to 25% porosity, usually 10 to 25%. So this is the log of conductivity versus temperature in degrees C, degrees F. And this is thermal conductivity on a log type scale. So this first one is dense MgO that has the highest thermal conductivity. And then as we lower the MgO content with chrome additions, the conductivity decreases from the top to the bottom here. So lower MgO content, you have phonon scattering, microstructural defects, and chrome is a lower conductivity material. So that's a trend for basic refractories. MgO's the highest conductivity, and it decreases with chrome additions. For the alumina silica refractories, again, maybe 0 to 25%, more realistically 10 to 25%. Dense alumina has the highest thermal conductivity. On this plot is dense vitreous silica. So this is fused silica, and you can see that this one has the 1/T relationship followed by the region where it tends to level out. This one is the radiation effect. It just increases with temperature. And then as we lower the alumina content on these materials, so the silica content's going up. As we lower the alumina content, the conductivities go down. So alumina has the highest conductivity. As we decrease the alumina content, because of defects, lower conductivity of silica, the conductivity decreases. So this is again more alumina silica materials, and these happen to be castables or monolithic materials. Curves 1 through 12, these curves in the upper part of the diagram are mullite alumina type materials. The curves 13 through 30 towards the bottom of the diagram are mullite silica type refractories. So if we look at the phase diagram for silica alumina, the binary phase diagram, and this is in mole percent. So the left-hand side is 100% SiO2, the right-hand side is 100% alumina. So the high alumina materials are going to be a combination of corundum, alumina, and mullite phases. The higher silica materials are going to be SiO2, either tritamide or cristobalite, and mullite. So there's a difference in the conductivity based on which phases are present. So material like alumina is going to have a high conductivity. Then there's mullite in this region here, has a lower conductivity. Silica crystalline quartz is down here. It has an even lower conductivity. And then the vitreous silica is down here, and then there's the radiation effect. But on that phase diagram, you go from alumina to mullite to silica to fused silica, the thermal conductivity decreases. These are dense refractories, and these are the monolithic materials. So these monolithic materials are in the mullite alumina part of the binary phase diagram. These materials are in the mullite silica binary part. So the conductivity decreases from alumina to mullite to silica to vitreous silica. And then the last slide here are alumina silica insulating refractories, both castables and fired refractories. These are highly porous, so all of these conductivities are increasing with temperature due to the radiation effect. So at any given temperature, the thermal conductivity tends to vary in a linear manner with the density. So again, thermal conductivity versus temperature, going up from bottom to top, the insulating fire bricks, the IFBs, they're going up in use temperature, they're going up in alumina content, and they're becoming denser. So at any given temperature, if you plotted conductivity versus density, it's going to be pretty linear. So we have insulating fire bricks are 28 to 60 pounds per cubic feet. Insulating castables are 45 pounds to 100 pounds per cubic feet. So there's a lower envelope of castables, a higher envelope, and then all the IFBs. They all fall in this range. They have very low thermal conductivities, high porosities, and the radiation is a big contribution to the thermal conductivity. So there's two common ways of measuring thermal conductivity of refractories. One is the water calorimeter. The other one is the hot wire technique. So I'll go over each one of those. In a water calorimeter, you have steady state thermal uh, conductivity conditions, and you generate a large thermal gradient across your sample. So this is a furnace. Um, this one has silicon carbide heating elements. Your samples are in the bottom part of the furnace. They're sitting on a water calorimeter. This is the cross section, the end view of 3 full-size bricks. Your test brick is right in the center over the center calorimeter. So there are 6 bricks that actually make up this plate, 3 full-size bricks, and then you have 6 half-size bricks. So a full-size brick was cut in half to form this plate, which is, I think, about 13.5 inches by 18 inches. So it's a pretty large plate sitting on these calorimeters. So these are water cooled. They're on the bottom of the bricks, and over the bricks is the furnace that's heated. There's a thermocouple that measures the temperature. And you can put a silicon carbide plate between the heating elements and the samples to improve the thermal uniformity. So this is the top view of that plate. There's 1, 2, 3 full-size bricks, and then there's the half-size bricks around the full-size bricks. So this is about 13.5 inches by 18. And the side view here, this would be a 4.5 by 3 inch or 2.5 inch cross section. The test sample has a thermocouple embedded in the hot face and the cold face. And then there are 3 calorimeters. The center calorimeter, which measures the heat flow, and then there's outer guard calorimeters that you adjust. So you have a uniform, steady state heat flow through this entire plate. So the calorimeter looks something like this. There's an inlet and an exit, and then there's all these water channels. So water comes in one of these inlets, follows these channels, and then exits. So there's your test calorimeter, which is about 3 inches by 3 inches. There's 2 inner guards and then the outer guard. So these are all adjusted so that the heat flow through the plate, that 13.5 by 18-inch plate, is uniform. So the center calorimeter is used to measure the heat flow. So water comes in at a controlled temperature and then leaves as it passes through the calorimeter at a higher temperature. So those temperatures are measured. So you measure the temperature gradient across the brick, which is the thermocouples in the hot and cold phase. You measure the rate of heat flow through the test brick through that center calorimeter. So you simply measure the mass of water flowing through the calorimeter in some time period, usually about 3 minutes. And you have thermopiles, very accurate thermocouples embedded in those inlet and exit channels. So that measures the temperature rise of the water flowing through the center calorimeter. So if you know the temperature rise of the water and the amount of water flowing for some time period and the heat capacity of water, you can get the heat flow. So Q, the rate of heat flow, just equals the heat capacity of water times the temperature rise across the center calorimeter, and that's the difference between the inlet and outlet temperatures. You measure the mass of water flowing during some time t. So that's your heat flow Q. And here's our equation for steady state heat flow. The thermal conductivity equals the heat flow times the distance between the hot and cold phase, and the area, which is the area of the center calorimeter, and then the temperature difference between the hot and cold phase. So very simple calculation. You can get the conductivity, and this is under steady state conditions and a very steep thermal gradient. The hot wire technique is a transient technique. The samples are sitting at a constant temperature, whereas in the water calorimeter test, the sample's under a steep thermal gradient. And what we learned about thermal conductivity, it varies with temperature. So in the water calorimeter test, since there's a thermal gradient from the hot to the cold phase, there's also a conductivity gradient. But in the hot wire, we're running at a constant temperature. So there is a difference between these tests. You're going to get different answers. So you just have to keep in mind the hot wire is at constant temperature. It's basically measuring the true thermal conductivity of the material at a constant temperature. And the water calorimeter is measuring the conductivity over a temperature and conductivity gradient. So it's an average conductivity. So the water calorimeter tends to give lower values of conductivity compared to the hot wire technique. So in the hot wire, you just apply a constant electric current to a platinum wire that's sandwiched between two full-size bricks. And then the rate at which the wire heats is dependent on how rapidly heat flows from the wire into the mass of bricks, which are held at a constant temperature. So if the bricks are insulating, the heat flow is going to be slower than if they're highly conductive bricks. So the rate of temperature increase of this wire is measured by measuring its resistance as a function of time. And then the thermal conductivity is calculated by the rate of temperature increase of the wire and the power that's input to the wire. So this is a schematic of the hot wire technique. You have a furnace. Inside the furnace is your sample. So it's two full-size bricks with a platinum wire between them. There's a gauge length where the measurement actually takes place. And there's voltage leads, platinum wires coming out, defining this gauge length. So you have to measure the gauge length L, and then you're measuring the resistance of this gauge length as a function of time as you heat the wire. You're using a multimeter to measure the voltage across this gauge length so you can get the current. And you put in the circuit a standard resistor, and you measure its voltage to get an accurate current flowing through the platinum wire. There's a power supply that provides the current. A multimeter measures the voltages and currents. And this is just controlled by a computer system that records the data and sends the appropriate power to the hot wire. And what the sample looks like, there's two samples. This is the bottom sample. The top sample is the same, except there are no channels for the voltage leads. So you have to surface grind a ledge into the sample. And on the top brick, you have the opposite ledge. So here's your platinum hot wire, which lays right along this ledge here. And then your two voltage leads, which defines this gauge length. They come out through the channels to make your measurements. So you put the platinum wire in here, then you place the top brick on top, and it looks something like this. So now you have a round platinum wire in a square channel, and these are machined in such a way that they fit almost perfectly. So you have very good joints here and a sandwich platinum wire. So if you measure temperature as a function of time when you apply a constant current to the wire, theoretically it should be this straight line. So temperature versus the log of time should be straight, but the actual experimental curve looks something like this. You do have a linear region where you take your measurement. So time 1 and time 2 corresponds to where it starts to become linear, and then time 2 and temperature 2 where it becomes nonlinear again. So you have a round wire in a square hole. So there's a wire sample contact resistance. So once that's overcome, it becomes linear. Then at some point, that thermal pulse that's generated by the hot wire reaches the outside of the sample, and then you have additional heat loss. So you measure temperature as a function of the log of time, you get this linear region. You know your two temperatures and your two times. So the conductivity equals Q, the power input per unit length of wire, and the derivative of the log of time divided by 4 pi, the derivative of temperature. So dln T dt. So we have our slope, dln T dt is the slope. We know our two times and our two temperatures, and 4 pi is a constant. We need Q, and Q is determined by our voltage and resistance measurements. Vs is the voltage across the standard resistor. V is the voltage across the hot wire. R is the resistance of the standard resistor, and L is the length. So from those measurements, we get Q, and off of that plot, we get the times and temperatures, so we can calculate the thermal conductivity. So those are the two common techniques for measuring thermal conductivity of refractories. And keep in mind that the hot wire technique is measuring what I consider the true conductivity, and the water calorimeter is measuring an average conductivity over a steep temperature gradient, where the thermal conductivity has to vary with the temperature gradient. So that's what I have on conductivity. So we did elasticity, thermal expansion, thermal conductivity. And the last property we need to go over is fracture. And we'll start this today. We'll finish it next Tuesday, and then we'll start on the thermal shock theories, which, as part of all those theories, have these four properties. So I'll define theoretical strength, and then there's two criterion. Actually, two criteria for failure. One is based on stress, one is based on energy. So there's a stress criterion and an energy criterion. I'll look at factors that affect strength and how strength is measured, and then structural aspects, porosity, grain size, and temperature all affect the strength. And then techniques that are not commonly used in refractories, but I think are becoming more common, fracture toughness and R curves. R curves is the crack growth resistance as a function of crack length. Any material, any refractory with a rising R curve means that the crack growth resistance increases as the crack size increases. So it's going to be a thermal shock resistant material. Any material with a high fracture toughness, resistance to crack propagation is going to be a good material for thermal shock resistance. So these techniques are important, so I'll go over those also. So for theoretical strength, this is actually the theoretical cohesive strength of material, sigma TH for theoretical. So we have a crystalline lattice. The circles are the atoms on the lattice positions. The separation, the atomic separation is A0. So we apply a stress, sigma theoretical, and we break those bonds. So now the interatomic separation A is much greater than A0. The bonds are broken. So the sigma theoretical is the stress required to break the atomic bonds and separate this material into two parts. So we can take a sine curve and approximate this force separation curve. So stress versus distance. The 0 point here between repulsion and attraction is actually where A0 falls. That's the interatomic separation at equilibrium. So you approximate the force separation curve with the sine curve, and this portion of the sine curve is lambda over 2, so it's half of a wavelength or half of a sine curve. So sigma equals the theoretical strength times the sine of 2 pi x over lambda. And this number here, 2 pi x over lambda, is a really small number. So the sine theta just becomes theta as an approximation. So the strength just equals the theoretical strength times 2 pi x divided by lambda. So we've determined that the stress equals the modulus times the strain, where we have brittle materials, and the strain is just delta L over L0. And in our case, it's X over A0. And then putting into this equation for stress, putting in the strain here, sigma equals EX over A0. And then solving for X just equals A0 sigma divided by the elastic modulus. Substituting X into our equation here, the strength equals the theoretical strength, 2 pi A0 times the stress divided by E lambda. And the theoretical strength just equals E times lambda over 2 pi A0. So we need to get an estimate of this variable lambda. So we equate the true surface energy to the strain energy. So 2 gamma S is the strain energy. That's the area under the force separation curve, under this curve here. So 2 gamma S equals the integral from x equals 0 to x equals lambda over 2 theta dx. And we substitute in our expression for sigma dx. I guess the theta, it's sigma dx. So from x equals 0 to x equals lambda over 2, sigma theoretical equals the sine of 2 pi x divided by lambda dx, and that you integrated it just lambda theoretical strength divided by pi. Solving for lambda, it's 2 pi gamma s over the theoretical strength. So we can put that back into this equation. And when we do that, the theoretical strength equals E lambda over 2 pi A, putting in the expression for lambda. We end up with this, the 2's cancel and the pi's cancel. So it's just E gamma S over the theoretical strength divided by A0. So the theoretical strength squared equals the elastic modulus times the fracture energy divided by A0. And if you take the square root of each side of this equation, our final result is the theoretical strength equals the elastic modulus times the fracture surface energy divided by the interatomic spacing, and that's all to the 1/2 power. So if we look at this equation, if we want a high strength material, we want a high elastic modulus, a high fracture energy, and a small interatomic spacing. So materials with high bond strength and high bond density have small ions, highly charged ions, high valence, and very dense packing in a crystal structure. So if you take that equation and you calculate the theoretical strength for some materials, and I have done that for alumina, silicon carbide, and glass, this is strength in PSI. Alumina is 5 million, silicon carbide is 6.8 million, and glass is a little over 1 million. So these are very high values. If you take a polycrystalline aluminum material and you go in the lab and you measure its strength, it's going to be 3,000 to 5,000 PSI. Stone carbide, maybe 25,000 to 100,000 PSI, and glass, maybe 15,000. So the real strengths are actually really much lower than theoretical strength. And in these brittle materials, why is there that difference? Is the presence of flaws. Flaws concentrate stress and reduce the theoretical strength to a much lower value. So flaws are stress concentrators. They cause fracture to take place at loads much lower than the theoretical strength. Flaws can be pores, they can be micro cracks, they can be scratches on a surface, but they're all some type of defect that really lowers the strength. And then I just showed strength can be in kilograms per millimeter squared, PSI, pounds per square inch, or megapascals. So this is the relationship between those different units. So that's the theoretical strength. The actual strengths are much lower because of flaws. So we'll consider a stress criterion and then an energy criterion. So in the stress criterion, we have stresses that are concentrated at the flaw tips. And as I mentioned, they're going to reduce the theoretical cohesive strength. So this is a plate that has some thickness T. And in the middle of that plate, we place an elliptical hole. So that's an elliptical pore or hole. The minor axis is 2H, the major axis is 2C. Rho is the radius of curvature at the tip. We apply some stress sigma A to this plate. We put it in tension. And if we look at the stress profile, at the outer surface, we have sigma A, but as we approach the tip of this ellipse, the stress is concentrated and it reaches some value sigma max. So the stress concentration for this elliptical hole, sigma max at the tip of the ellipse just equals 1 plus 2C over H times the applied stress. 2C is the length of the ellipse, 2H is the height of the ellipse, sigma A is the applied stress, and then the stress that results is the maximum stress at the tip of the ellipse. So if C and H are equal, we basically have a circle instead of an ellipse, so that's 1 plus 2. So the maximum stress is going to be 3 times the applied stress. So sigma max is at least 3 times the applied stress. But as we close this circle down to form an ellipse, this value goes up much higher. So the maximum stress is a lot higher than 3 times the applied stress. And if we take that elliptical hole and compress it, we can have a crack. So we have an atomically sharp crack instead of an ellipse. So the radius of curvature at the tip of that crack is H squared over C. H squared then equals rho C, and H equals rho over C to the 1/2 power. And we put that into our equation here, put in H, and so sigma max equals 1 plus 2C divided by rho C to the 1/2 power times the applied stress, or more simply 1 plus 2C over rho to the 1/2 power times the applied stress. C over rho is a high number, much greater than 1, because the stress concentration at the flaw tip is high. So we can eliminate the 1 in this equation here because 2 times C over rho to the 1/2 power is much greater than 1. So the maximum stress simply equals 2 times C over rho to the 1/2 power times the applied stress. This is a large number. So it turns out the maximum stress at that tip of that crack is going to be 100 to maybe 2,000 times the applied stress. So there's a great deal of stress concentration at an atomically sharp crack. And that's why there's a big difference between the theoretical and the actual strengths. So this stress criterion shows us the stress concentration at flaw tips. The stress concentrations reduce the theoretical strength. It's just telling us stresses are increased around a flaw, but what it doesn't tell us is when fracture is going to take place. So it doesn't show the necessary condition for this crack to grow at that point or tip of the atomically sharp crack. It just tells us how the stresses are concentrated. So the second part of this is the energy criterion. So this tells us when a flaw will propagate. So flaws propagate when the decrease in the stored elastic strain energy associated with crack extension exceeds the increase in surface energy associated with the new crack surfaces. So the stored elastic strain energy is the energy that is being converted to fracture surface energy. So this type of approach shows the necessary condition for the cracks to grow and cause failure. So now we have another plate of thickness T, and we apply a load to that plate. Then we insert an elliptical hole in that plate of length 2c. So when we do that, there's an extension of the plate, a distance x, because we introduce this elliptical hole. So the energy criterion is based on an energy balance. So the total energy of the system is TE. That equals TE0. TE0 is the energy of the uncracked plate with no elliptical hole in it. And then US is the increase in the cracked surface energy as a result of the elliptical hole. UE is the increase in the stored elastic strand energy, the plate extended, and W is the external work performed. So the total energy of the system equals the energy of the uncracked plate plus the increase in the cracked surface energy plus the increase in the stored elastic strain energy minus the work performed. So US is the fracture surface energy term. That opposes crack growth. UE minus W is the potential energy term. This is the driving force for crack growth. So now we allow the crack to grow a distance DC from each one of these tips, opposite tips of the elliptical hole. So now we have a delta U. The first displacement is U1. When we allow the crack to grow, there's a further displacement to U2 or mu2. So delta mu is the change in length. So delta mu equals mu2 minus mu1. So it turns out the work just equals 2 times UE. UE is the increase in the stored elastic strain energy. So if we plotted load versus displacement on the elliptical crack has a length of 2c, the displacement is mu1. So this is the load displacement curve. And then when we introduce the crack DC, it increases the length 2c by 2dc. It has a new displacement mu2. So this is the corresponding load displacement curve for the second situation. So the work just equals the load times the difference mu2 minus mu1. And then the stored elastic strain energy is the difference between the area under these two curves. So 1/2 mu2 times P minus 1/2 mu1 times P. So the stored elastic strain energy is equal to 1/2 P and the difference mu2 minus mu1. So if you look at this equation and this equation, UE is 1/2 of W, so W equals 2 UE. So we can put W into this equation in terms of UE. So we simplify the equation. The total energy equals the initial total energy plus US minus UE. Then US just equals the area times gamma S. So we can approximate the area by opening up this elliptical shape. So this is the thickness of the plate T. This is the major axis of the ellipse 2C. We open this up. So now I have T, and then this length is approximately 4C. So the area is simply 4C times T. And if we multiply that by gamma S, the fracture surface energy, US is 4CT gamma S. And we put that into this equation for US. So TE equals TE0 plus 4CT gamma S minus UE. And gamma S is the fracture surface energy. So now we need the last term here, UE. That equals 1/2 sigma A squared over E. And there's a volume term. So this is the volume of stored elastic strain energy. So here's our elliptical hole. The dotted ellipse around this elliptical hole represents the volume that's stressed. So this is 2C, this is 4C. So the area of this volume that's stressed is 2 pi C squared. And then it has a thickness T of the plate. So the volume is 2 pi C squared T. So UE is 1/2 the applied stress squared over the elastic modulus times this volume 2 pi C squared T, which is right here. So you simplify that, the 1/2 and the 2 cancel. So UE equals sigma A squared divided by E pi C squared T. And that is put into this part of the equation here. So now we have our final equation for the total energy of the system in terms of the fracture surface energy and the stored elastic strain energy terms. So this is our equation. If we plot total energy versus crack length C, this curve, the straight line here is US, that's 4CT gamma S. This part, when it's plotted, UE is just minus sigma A squared divided by E pi C squared T. The sum of those two, and we're starting at TE0, is this dotted line. So there's a maximum on this curve for the total energy. That maximum occurs at what we call C star, the critical crack length. So this is a constant slope. This curve, as we increase the applied stress, is going to shift in the downward direction. And at some point, the maximum in this total energy curve will hit the critical flaw size, and then fracture will take place. So fracture takes place when the applied stress is large enough that the total energy exceeds this critical flaw size. So fracture takes place when the total energy of the system decreases. So the condition for the increase in the flaw size, where the flaw size C becomes greater than this critical flaw size, is given by this equation. We take the derivative of the total energy with respect to the crack size. That equals 0 plus 4 T gamma minus 2 sigma squared pi CT over E. We solve for C in terms of C star, 2 gamma SE divided by pi sigma A squared. And then we solve for sigma A And since it's at the critical flaw size, it's now sigma F for failure. So the fracture stress at failure equals 2 times the fracture surface energy times the elastic modulus divided by pi, the critical flaw size. This is all to the 1/2 power. So this is a very famous equation known as the Griffith equation. It's telling you the actual condition for the cracks to grow or failure to take place. So if you know the fracture surface energy, the elastic modulus, there's a critical flaw size in the material. That corresponds to the strength needed to cause failure. So you must reach this critical strength, sigma F, that's associated with the critical flaw size. So very simply, sigma F is the stress level required to propagate that flaw to grow this critical flaw size C star and cause failure. And at that point, the energy of the system is lowered. The strain energy is being converted now to the fracture surface energy. And one other thing we want to get out of this equation, we started out with this equation, we took derivative, and it is basically 0, setting it equal to 0, and then eliminating the 2, and the 4 becomes a 2 here. 0 equals 2 gamma S. We also eliminate the thickness T minus gamma sigma A squared pi C over E. I don't know why I'm calling sigma gamma today. This term, 2 gamma S, is known as R, the crack resistance. This is what's used in the rising R curve equation. So the derivative of the fracture surface energy with respect to the crack length is the crack resistance R. The derivative of the strain energy with respect to the crack length is G, the strain energy release rate. So that's gamma sigma A squared pi C divided by E. So these are important fracture mechanics terms. The crack growth resistance R and the strain energy release rate G. So the higher the R value, the harder it is to propagate a crack, the better the thermal shock resistance. And in thermal shock resistant materials, we have what's known as rising R curve. So as the crack grows, the crack resistance increases, the R value increases. So if we go back to our total energy versus crack length plot, here's our C star, our critical crack length. This is the fracture surface energy plot for CT gamma S. This is the stored elastic strain energy part minus sigma A squared over E pi C squared times T. When R equals G, that's the equilibrium point right at the critical flaw size. Below this flaw size, the crack growth resistance is greater than the strain energy release rate. So R is greater than G. We're in a stable situation. The crack doesn't grow. But when G becomes greater than R, this becomes unstable and failure takes place. It's just another way of looking at this type of plot in terms of the crack resistance and the strain energy release rates. So if we plotted these energy rates versus crack length, it would look something like this. Here's our critical flaw size again, C star. Here's R. This is a flat R curve. R equals 2 gamma S. This is typical of brittle materials that have poor thermal shock resistance. So R is a flat curve, it's a constant. And then this is G, sigma squared pi C over E. So as we increase the stress, this, this curve actually starts out down here and moves upward. And when it crosses this point here, that's the critical strain energy release rate at the critical fracture stress. So G becomes greater than R and fracture takes place. And we'll go over this next class where we have materials that exhibit rising R curves. So at this point here, if we have a rising R curve, it goes up like this. So it becomes more stable and it takes a greater G to cause failure. So it becomes more thermal shock resistant, or it becomes also stronger. So the magnitude of flaw sizes in refractories, well, flaw sizes are comparable to the coarser features in the microstructure. And because of the thermal mismatch between coarse aggregates and fine aggregates, or multiple types of aggregates in the matrix, the coarser features tend to be the flaw sizes. So they range from maybe 0.2 millimeters to 10 millimeters. So these are the pre-existing flaws in refractories. They're responsible for the low strengths. And when you measure strengths of refractories, you'll see quite a bit of scatter. That's because of the variability in the flaw sizes. So we'll just go over 3 and 4 point bending and finish the lecture today. This is a 3-point bend bar. It's the typical way we measure strength of refractories. We have 2 loading points, or loading edges. They're separated by a distance L, so that's the lower span. There's a loading point at the top where we apply our load P. Sigma F, the fracture strength, equals 3PL divided by 2BH squared. B is the width of the sample, H is the height. So this is loaded until failure takes place. So this is a failure in tension, but the bar is only really in maximum tension at the bottom surface here. Top surface is actually in compression, and then the middle plane here is neutral. It's neither tension or compression. So 3-point bending is a tensile failure, but it's not a pure tension. It's got a maximum tension at the bottom surface here. And if we look at the bending moment diagram, so here's our lower span L. This is L over 2 right at the center point where the load is applied. The bending moment is PL over 4. It's 0 at the bottom knife edges, and it's a maximum at the top knife edge, and it's linear relationship. So the maximum bending moment is right at the center of the sample. So only a small portion of the sample is subjected to the maximum bending moment. So you have some type of flaw size distribution in here where the flaw size is variable. So it's only sampling a small portion of the sample. And if your most critical flaw size is right at the center point, that's where failure may take place. If it's over here somewhere, failure may take place off center. The other way of measuring strength is a 4-point bending bar. So now you have L again for the 2 lower loading points. And now there's 2 upper loading points separated by another span, small l. Each one of those has the load P over 2 because there are 2 loading points. So the equation for failure, sigma F equals 3P, capital L, the lower span, minus small l, the upper span, over 2BH squared. And B again is the width and H is the thickness. So if we look at the bending moment diagram here, this distance is L, the shorter distance is small l. So the maximum bending moment is P, L minus L over 4. But if you notice, between the two top loading points that span L, we have a constant bending moment. So now we have a constant bending moment over a large area here. So if there's a critical flaw in here, it will be the flaw that's responsible for failure. So because this is a bigger volume under a maximum load, it's going to give you a smaller strength because you're going to find a more critical flaw in this bigger volume compared to this really small volume under the maximum load. So a 3-point bend test is going to have more scatter in the strength measurement, and it's going to have a higher strength than a 4-point measurement, which is going to give you a lower strength but less scatter. So more commonly, this is the easiest strength to measure a 3-point bending strength, and it's also the easiest to do at high temperatures. So this is the most common in refractories, but if you want to have a constant bending moment, you would go to a 4-point bending and actually see lower strength values, but more uniform values. So I think I'll stop there. And next time we'll finish up next Tuesday, strength, and start on the thermal shock theories. So hopefully you all got the corrected version of the thermal expansion lecture. So thanks for attending today, and have a good weekend, and I'll see you next week. Thanks again.
Thank you.